Hi all. In this video, we see a paper titled Switching Sampling Space of a Model Predictive Path Integral Controller to Balance Efficiency and Safety in Four-Wheel Independent Driving and Steering Vehicle Navigations. So, this paper is about using MPPI algorithm, namely Model Predictive Path Integral Controller, for path tracking and autonomous vehicle, especially four-wheel independent driving and steering vehicle navigations. So this paper says that four-wheel independent driving and steering vehicles have some potential advantage for the future generations because it can independently control the steering angle and driving torque of all wheels, enabling holonomic movements such as pivoting in place and diagonal movement. So it has 8 degrees of freedom, one for wheel, two for each wheel, and generally for autonomous systems for these kind of vehicles, gradient based model predictive control is effectively used, but unfortunately this mpc has to handle non-differentiable cost functions, and also because of nonlinearity it may ended up in a local minima. So hence therefore sampling based model predictive path integral control has a wide promising directions for addressing this part tracking methods for this particular special vehicles. But unfortunately, this has one critical negative factor issues, namely the curse of dimensionality. As number of input dimensionality of the input increases exponentially, there would be a possibility of decreasing sampling efficiency, which we'll be defining in later sections of this video. So to address this curse of dimensionality, one usually try to reduce the input dimensional space into a reduced space and try to use this MPAPA algorithm for the part tracking controller. So in this paper has some threefold primary contribution. One is to try to reduce the dimensionality of eight input dimensional space of this four-wheel independent driving and steering to three independent dimensions. But unfortunately, they have some critical issues while using the MPPA with three dimensions. So they try to make a second contributions of slightly increasing this dimension to four dimensions with a redundant input space, which feels that they have some better efficiency compared to these three dimensions. And the third contributions would be that they have a hybrid approach that input dimensional space can be switched based upon the situations while doing a real-time computations, which also we'll be discussing later in this video. So this related to this control approaches for this four-wheel independent driving and steering. Fuzzy logic has been utilized in the paper 19, and also they have used a MPC has been widely used, but as mentioned earlier, the MPC is computationally expensive, and they have to go for linear approximations to avoid local minima, and also has to go for a cost function or objective one, which should be of a differentiable nature to use the gradient based MPC thing. So, sampling based solver like MPPA has giving a promising approaches, and one of the simplest of using this MPPA is to uh, sample several sequences and evaluate them to find the best one, and the best one can be utilized as a MPPI based path tracking controller. But unfortunately, this can have a huge drawback of low sample efficiency, and since we are using the best one single shot in a stochastic algorithm, it can be result in a jerky navigations. So MPPA is utilizing the bunch of samples, and the averaging one is being utilized for tracking, which can generate a smooth behavior. There are also attempts that have make a combination of MPPA with reinforcement learning in paper 22. So the objective of this paper is to navigate this four-wheel independent driving and steering vehicle to a given goal. At the same time, avoiding collisions with the surrounding obstacles using the best MPPA algorithm. So the global planner generates a reference trajectory, and the local planner MPPA is utilized to follow the reference trajectory while safely avoiding the obstacles. So these obstacles can be of densely populated as necessary to have some small turning radius and diagonal movement, at the same time maintaining a smooth and efficient driving. This is our fundamental objective, and the characteristic of the vehicle motion is also a four-wheel independent driving and steering vehicle behavior. So the model can be comes from the nonlinear Newton's law of motions, giving the characteristic of the tire eight tire characteristic. But unfortunately, this can lead to a huge complex model. But to avoid that, we this paper has utilized a simple kinematic assumptions where it has reduced to a 3 degrees of freedom. But there is transformations from 3 degrees of freedom to the 8 degrees of freedom using this C to 8 matrix. And this once the 3 degrees of freedom is computed from the MPP algorithm, then this matrix can be utilized to transform to the full degrees of freedom. That full degrees of freedom can make a nonlinear conversion of FE to convert into the vehicle controller, and that vehicle controller can be input to the actuator to make a next observe the next state. So this is the fundamental basis, but unfortunately, three independent degree was not that more effective. A slight that would be mentioned in the later in the section 6 or 5, and so there instead of 3 degrees of freedom, 4 degrees of freedom is utilized, and 4 degrees of freedom can be make use of that to convert into 8 degrees of freedom. That 8 degrees of freedom, as usual, on nonlinear model can be utilized to give an input to the actuator. So this is what it describes the architecture. It has some four components as mentioned here. First is state observation, then global path planning, then local path planning, then vehicle command calculations. So the states will be observed and the global path planning will be computed. That both things will be given as input to the MPPI. The MPPI will based on a 3 degrees or 4 degrees of freedom try to compute the optimal input values. That input values may be either 3 dimensional or 4 dimensional, which would be that transformation matrix C3 to 8 or 3 C4 to 8 would be transferred, and that nonlinear transformation will be converted into the vehicle controller. That vehicle controller will be given to the actuator to actuate the four different wheels of velocity and the angular velocity. So this is the objective, and we just in the algorithm one is beautifully explained about what is MPPI, which will be coming now. So MPPA algorithm one is the first one is to compute the optimal control as mentioned earlier, either in 3 degrees of freedom or 4 degrees of freedom. First, it does involve in a sampling process using a normal distribution centered around the previous optimal input sequence. That on optimal input sequence, that sample trajectory will be weighted some, so that the better sequences are heavily weighted. And so if there are 20 trajectories are sampled out, then each trajectory will have some own weight factor based upon certain criteria, and then weighted average will be give the optimal sequence, and that optimal sequence will be given to us a controller input. So now we'll have a k samples of input sequences of adding a Gaussian noise to that to the mean control input with the covariance matrix. After preparing the samples, the optimal control input sequence is easily obtained by calculating the weighted sum of these samples. So this weighted sum is based upon the total cost of the kth sample. The total cost would be depend upon the terminal cost and the stage cost, and this is the calculation for the weight factor, which depends upon the total cost. The total cost depends upon the stage cost and the final cost. So this notable benefits of MPV are that it can be applied to a wide range of organization model, including nonlinear, non-convex, and non-differentiable cost functions and system models. The algorithm is theoretically guaranteed to minimize the KL divergence between the proposed distribution and the optimal distribution, which minimizes the total cost functions. So one of the other third contributions would be that how this MPPA can be switched between different control spaces. There will be a two MPPA algorithm can be developed, one based on 3 degrees of freedom and 4 degrees of freedom, and there can be a criteria that 3 degrees of freedom or 4 degrees of freedom can be used in an MPPA based, and that will be making into a transformation matrix to a full 8 dimensional, and that will be given as a vehicle control input. So this is the path MPP algorithm, and we will be inputting the kinematic model F and G transition model. Then we'll choose the number of samples K can be 20 somewhere, and total number of time steps to be done. Then we'll have the initial control sequence, and these are some of the hyperparameter that has to be chosen. And then while certain criteria has not been satisfied, we'll be iterating through all these 20 samples, and through all iterating through all the time steps, and at each time step we'll be computing the total cost, and total cost will be accumulated, and that accumulated total cost will be utilized for the weighting factor, and the weighting factor can be utilized to in the sampling, that noise sampling will be added into this to have a total and optimal better input sequence. That input sequence can be converted into 8 degrees of freedom, and that vehicle computer vehicle input will be given to the actuator for actuating, and then next state would be observed, and this will keep continuing. So this is the MPPA algorithm, and the cost functions that we have it has been utilized here would be that based on that how deviate from the how this current vehicle is deviated from the path, and how much it is deviated from the angle, and how much it deviated from the expected or nominal speed, and how it could able to proceed without collisions, and also the smoothness of the command, not having any jerky behavior. So each one has its own weights, and these will be the hyperparameters, and which has to be given weightage has to be decided during the process. And the collision factor is a binary, like 1 is for collision, 0 for no collisions. And this would be for the smoothing factor, which should not be deviate much higher than the previous one. So this helps us to prepare the MPPA one. But now here the thing is how MPPA using 3 degrees of freedom, 4 degrees of freedom, and hybrid, like switching the 3 degrees of freedom to 4 degrees of freedom when the necessary criteria is reached, is been compiled uh, here. And we have two types of MPPA 3D based on the variance. One is high variance and one is the low variance. So these are the results being observed here. These are the criteria to select the mode when based on the distance and the angular deviance from the track angle. So what we observed is the MPP3D has a very aggressive behavior. It could finish it in a short time, but it has more aggressive, and it can able to collide, make collisions in both on the. So sorry, I have to mention about the simulation environment is a Casilo simulation environment, and both the cylindrical and the maze, and we have 10 goals sequentially arranged, and then this has used a ROS and C++ environment with i7 processor. And this is the environment that we have been utilizing. These are the 10 goals sequentially arranged and switching from one environment to the other environment. So as mentioned earlier, we compare like four different 3DA, 3DB, and 4D, and hybrid, switching from 3D to 4D degrees of freedom. And 3DA is a high variance. When we are using high variance, it has a short time, but it's very aggressive and leads to a large number of collisions. 3DB is much smoother than 3DA, but it has the low variance. And 4D is much giving a better promising one, and although it's slow in time, but it is very robust and doesn't have any collisions during the process of reaching the goal. But additionally, we can use the efficiency in time and also in safety and stability, and use a hybrid mode when to switch between the 3D and the 4D, giving promising directions. So these are the trajectories are compared in the figure 6a. 3D he is giving some kind of large curves and is very close to the collisions, and 4D could be able to turn in place and it can have a smooth behavior. And hybrid, both 3D and 4D is here, and when making an aggressive turns, 4D is activated, and when having a straight run, it can go in a high speed with the 3D getting activated. So this is the discussions we can have, because the reason for the 3D to behave bad is because Jacobian matrix of 4D is more sparse, and it gives you a very this velocity translation and the rotational velocities are becoming almost independent compared to the 3 degrees of freedom. That is one of the observations they observed through the analysis of the mathematical behavior of the Jacobian matrices, both utilizing the 3D and the 4D. So final conclusion is, yeah, this paper is very beautifully written about the MPPA controller, and this has been utilized for the four-wheel independent steering and striving. And the author claims that this is the first paper to utilize MPPA for the four-wheel independent steering and striving. And the results observed is that for you can make a reduce, although initially it's an eight dimensional input, we can reduce to a three-dimensional, four-dimensional input. Four-dimensional gives you a more stable behavior, and better efficiency can be achieved when we have a hybrid mode, and when to switch between the 3D and 4D mode based on the rotational requirement in the four-wheel steering. Thank you.